Awesome. Thank you so much. And this is a great initiative. I want to kind of start by saying that it's amazing to have a forum like this. Okay, so let me just share my screen. I want to kind of talk about security architecture in general. I'll start by introducing myself. So my name is Ashwini. There are a few different parts of me that I'd like to kind of talk about, basically because I feel like I spent most of my initial years kind of focusing on the left brain. That's like the engineering side of things. But I do also have a poetry blog. And then right now I'm in the phase where I'm trying to bring both my left and right brain together. I work for an early stage startup called DevRev. And I also host a podcast. But a little bit more about my engineering journey, which is, I'm sure, what the group would be more interested in. I'm currently am focused on the product ideation and architecture for the early stage company called DevRev. But I do have a fair bit of experience, probably more than a fair bit of experience, coming to think about it, in software development and architecture and across multiple different domains. Across like embedded systems, I've worked on radio frequency systems for mobile phones and on-prem infrastructure, quite a bit on the security area as well, more from the angle of building a security product at my previous employer, Nutanix. I do also work on application software. And I think when I think about security, I kind of view it from multiple angles at the moment. One, in terms of what it took to develop some of these security solutions, and also from the angle of, okay, so now as someone who needs to secure their application, how would you go about doing it? You can potentially build everything from scratch, but then given that I know what it takes to build it, I probably wouldn't make that choice for every single one. And I'd love to kind of have a discussion around that as we go through the presentation. I do also have experience working in kind of all sizes of companies, so it's given me an interesting perspective. All right, that's enough about me. Let's talk about the actual topic on hand. The way I'm planning to structure this, or the way I have structured this talk, is around, why do we need security? Why, in the first place, why are we doing all of this? And then what is it that we're trying to secure exactly? And finally, how do we go about securing it? And you'll see this huge list when I say, how do we secure it? Essentially, because there's so many angles to consider. And of course, this is not an exhaustive list, right? There's so many other angles that are probably left out. But I'm hoping that we'll at least skim the surface on some of these and also have a slightly deeper discussion on each of these topics to understand them better. I do want to kind of start by asking you to please, probably in the chat or signal in any way if you feel that I'm, going into too many details and it doesn't seem to make sense, or if it's, too superficial and you'd like to go into more details. But starting with why security, I think a lot of us have seen news articles, whether it's like Equifax or it's the target data theft, or more recently, the Log4j breach. And this leads to a lot of angst, right? I mean, one is there's loss of customer data. So obviously customers are kind of very concerned about this. There's loss of credibility for the company. There's also the financial loss angle in terms of, just the lawsuits and how much, for example, Equifax ended up losing. There's also financial loss when we look at it from a systems architecture point of view. And what I mean by this is, if you look at how we structure most of our cloud systems today. So if, for example, you are an AWS customer and you started using AWS Lambdas and you suffer a denial of service attack, and we'll quickly go into what denial of service attack is. But let's say it's a way for some of your it's a way for the attacker to kind of gain entry into your system and spin up these lambdas. Now, all of us know that lambda is basically something which you're charged for in terms of how long you run it. And that's a very easy way for you to go bankrupt, because if somebody takes control of that and then just start spinning these up, you're going to run up a huge Amazon bill, right? So that's financial loss as well, in terms of your systems being hijacked for processing, not just for data. So I'll assume that we're now convinced that we need security. We need to kind of prevent those adverse consequences. So we'll talk about what do we want to secure. Now, I've kind of taken a particular architecture. Of course, there are various different ways in which you can architect your product. But in this particular example, I've kind of assumed that you have an entry point into your system, and that entry point is the API gateway. So it's a load balancer come API gateway, let's say, which is the entry point into your system. And that's the only piece that is public facing. So that faces the internet or anything external from your cloud. And then you have a bunch of these services, so everything in blue is inside your cloud, inside your system. And each of these services could possibly be a microservice, which is building out a certain part of your application. And it sits behind the gateway. And then, of course, we would have a database as part of our product or solutions. So the database as well is within your cloud. Of course, you could be using an externally hosted database for certain use cases. So that's a possibility as well. And as we can see, there are interactions all around over here, right? So there's this one part of the interaction that you see where an API request or any kind of external interaction that's coming into your product from outside. And then there are various interactions which happen within within the cloud or within the perimeter of your product. Now, the philosophy of zero trust is that we treat everything the same. So just like you would treat an attacker who's external as a huge threat and try to secure the boundary. And I often take this example where I say, this is kind of like building a fence around your house and saying, okay, so I'm protected because I have this fence around the house, and so the boundary is safe. However, we know that there are various attacks that could actually be internal to your system. What I mean by that is maybe somebody accidentally downloaded, some kind of a virus, and that kind of penetrates your entire system and compromises the entire product. Or it could be, someone who inadvertently does something which ends up turning into an attack vector. So essentially, by applying the security policies and also, the security protocols, both within and outside the same way, you would be guarding yourself against both of these kind of attackers. So let me start with talking about the periphery or the gateway. So this is the fence equivalent, right? So of course, there are various levels of protection. I'm starting with the network access control lists and the firewall. This is usually the first level of defense in some sense. It's the periphery, like it's typically kind of just the entry point into your product and possibly even outside of your product. And this involves a few things. And I don't know how many of you over here have a networking background, but essentially this involves a few very, very specialized rules to be written, which are called access control lists. And it also defines a boundary within which you operate, a network boundary, which is called VPC. In Amazon, it's the virtual private cloud. And then you start writing rules about what do you want to allow access to from within this particular network boundary that you've defined. And so as you can see, it becomes fairly complex because then you have to deal with IP addresses and subnets and then trying to figure out exactly how do you write these rules. And this could be a non-trivial exercise, but this is usually the first level of defense. It's by no means foolproof. It's not like we have this in place, we're done, right? So going to the next level, we spoke briefly about denial of service. So essentially what denial of service means is that somebody starts bombarding you with a huge amount of requests. Now, as we're going to see later in the talk, there are mechanisms you can put in place to figure out, excuse me, how to authenticate the user, how to figure out if it's a valid user, trying to do a valid operation, etc. But all of that is going to take some amount of processing. So if you're going to be bombarded with a bunch of requests, you could just be, out of resources trying to handle those requests and then do this authentication or, the security protocol procedures. And so that's where the concept of a web application firewall comes in, where they're able to actually identify such malicious activity based on some predefined signatures, which keep evolving based on the threats and how they surface up. And they're able to block that traffic. So it doesn't even hit your product entry point in some sense, right? So it doesn't hit the API gateway that we spoke about. It's thwarted at a layer before that. And that's how, for example, you could do something called rate limiting and also avoid these kind of malicious attacks. Again, just another layer, and we'll continue to peel the onion. So now talking about authentication. So this is the piece which is going to define who you are, right? Who is the person who is trying to access your access anything. So they're making, let's say, an API request. Maybe they're trying to get data about some person's profile, right? So you want to know who is this who's trying to get data and should I allow them to get it, right? So these are two different questions, but we'll start with who you are, and that's the authentication piece. Now, there are various different ways of doing authentication. Some of them have kind of been an evolution. And the reason all of these exist in kind of parallel in some sense is that one, I guess products are in different stages of evolution. Depending on when you actually built your product, you probably used a mechanism which was current at that point of time. But also in terms of simplicity of how you could implement it, these things really vary a lot. So we're going to look at these in a little bit of detail. Again, please let me know if this is too much of detail or too less. So talking about basic auth, right? So basic authentication is, I think, what most people are just familiar with in terms of interacting with the product as a user. So this is where you give your username and your password, right? But the way the protocol works between a client and a server, trying to kind of basically use basic auth, is that they send this username and password in a base 64 encoded fashion, which basically means that it's fairly easy for you to crack it or to kind of decrypt it. I'm sorry, it's not even encrypted, it's just encoded, so decode it, right? So you can decode it and then fairly easily figure out how to enter or breach another system. Of course, if you use SSL, which we'll discuss in terms of certificate-based authentication as well, then your transmission or your medium is actually encrypted, and then that gives you a level of security. The next mechanism is something called a bearer token. So this is kind of a step up from the username and the password, right? So what happens in this case is the user signs in, and there is a concept of something called an identity provider or an auth server, which generates this token, which we call a bearer token, basically because the bearer of the token is allowed to access the system, right? And so this ID, the identity provider would basically generate this token. We'll look at the token in a bit, but generated uniquely for each user who's signing in. And then the user takes that token and tries to access your system. Now, one thing to note over here is that the generator will basically use a key, a private key, to be able to sign the token and make it secure. And the way that the server, or basically your server in the product, would actually go ahead and figure out whether it's a valid token is by using the public key corresponding to that key which was used for generation to verify that the token is valid. So this is a bit about how the token itself looks, right? Like what does this token actually have? So it has a header, it has a payload, and then it has a signature, which is basically going to run an algorithm on the header and payload to make sure that it is secure, right? And it can be validated. Now the header will tell you the algorithm, it will tell you the type of token it is. The payload can actually have, it can have custom fields, but it usually has some set fields like who issued this token, right? Like who is it issued for? And who's the audience? Like who are the people who are allowed to access resources based on this particular token? And this is another interesting one where it says expiration time, right? So you're not going to hand out this token and just say, that's it. I mean, you can access my system forever. Instead, you're going to say, you can use my token for, let's say, an hour, and then you'll have to come back and ask me for another token to get it refreshed. Because I'm not going to give you access for a long, there are kind of downsides of giving access for a long period of time, because revoking it then becomes really hard. And also, if your token gets compromised for some reason, then you have no way to recover from it. So some things to keep in mind if we go with the bearer token approach is that, like I mentioned, you could have custom claims, but we want to make sure that you don't have like a huge amount of data that you put over there. And also, you don't want to put sensitive information over there within the token that can be easily decoded. And we should use HTTPS, like secure communication, for the headers. And you would have seen that there is an algorithm mentioned over here. But the advice is basically not to just go by what's mentioned but actually verify that that's the algorithm that was used, because somebody might have spoofed it or done an attack to kind of change it. And if it's persisted in cookies, the advice is to mark it as HTTP only, basically because you don't want your browser JavaScript kind of reading this token and then misusing it for something from the cookie. Now, coming to certificate-based authentication. The way certificate-based authentication works is that your browser and so essentially your browser is the client, right? And the web server basically trust something called a certificate authority. So a good example or a parallel over here is we all trust the DMV. So when the DMV issues us a driver's license, then everybody accepts that that's a valid identity proof, right? So similarly, the web server is basically going to get a certificate, which is signed by the certificate authority. And the client, when it talks to the server and receives this certificate, is going to trust that certificate, basically because the client trusts the certificate authority as well. And so the certificate is used as a proxy for the server to prove its identity to the client, that it is a valid server that's actually that the client can connect to. Now, the OpenID Connect one is probably, I would say, in the stages of evolution. This is probably more current than all of the rest. And the way this operates is, if you have a web application, you get your request to the web application actually gets redirected, and it goes through. Maybe you could go through, one of these providers. They're called single sign-on providers. So I'm sure all of you, many of you, have actually encountered this, where you'll see this login screen where they say, "Hey, you can log in using your Google or using your Facebook." or using GitHub. And so that is a single sign-on, which essentially means you don't need to again create a login username and password. They will use your identity, which is provided by Google or Facebook, to authenticate you, right? And so given you, let's say for the simplest case, let's say you provided some kind of a password and then you got directed. And what happens behind the scenes is that they reach out to something called an OpenID Connect provider, which in turn reaches out to the identity provider that we spoke about before to be able to get a token. And here, this protocol basically beefs it up and says, it's not just a token, right? I will first give you an authorization code. And then based on that code, if you send that back to me and there's a way to kind of send it back in a secure way, and then I am convinced that it's you, then I'll send you a token, right? And then I will send you two kinds of tokens, one which is called the identity token, and then another one which is called an access token with different expiry times potentially, and then you could use those, right? So a little more complicated and probably hidden from the customer if they are using something called a something similar to a single sign-on provider. Now, that was authentication, right? So we spoke about 3 or 4 different mechanisms that you can use to do authentication. One thing I'd like to note over here is, I think there are always, you could implement these protocols for sure. There are RFC standards available and you can actually build these out. And I have spent some time building these as well in different scenarios because we were an infrastructure provider. But it depends on the focus of the product. So if you're building a product which is not in the security space, then you have ample other softwares that you could actually leverage for this kind of integration. So using something like Okta or Auth0 would actually provide this to you out of the box. Now, coming to authorization, right? Like, so we spoke about who you are. Now, what can you do, right? Like, we figured out who you are, but we need to see whether we'll give you permissions to do everything or we should restrict it in some way, right? And that's where the authorization piece comes in. And broadly, it's understood using these 3 structures, right? Like, it's the identity, and then it's the role that the identity maps to, and then it's the policies that you want to define on those roles. And essentially, if you take this example, so the identity could be, user 1, user 2. You could group a bunch of these users and say, hey, all of these, this entire group is actually corresponds to this role, right? A role of an architect or a developer or a tester. And then to that particular role, I want to apply certain policies. So maybe I want to give access to a particular kind of document repository to the architect and a different kind of repository to the tester, right? So that's where the authorization comes in. So this is also commonly referred to as role-backed access control, RBAC. Now, one of the things that's come up is, okay, so this is great. Now, how do we write these policies, right? And one of the new paradigms is the open policy agent. So if your product is built using Kubernetes or any kind of service mesh or any of these technologies, open policy agent can be hooked into it. Now, what the policy agent believes, the architecture essentially is to decouple the policy writing from the actual policy decisions. So what it does is you can send a query and a decision to the OPA engine, to the Open Policy Agent engine. And the engine will basically have a bunch of policies written, right? And then it will act on the, it will actually act on the query and then figure out the decision to be handed out. So you will send in a query and you will basically have the engine apply a policy to it to figure out whether the access should be allowed or not. So just to make things a little more concrete, essentially you could ask questions like which users can access which resources. You can also say, which subnets egress traffic is allowed or not, which clusters a workload must be deployed to, which registry binaries should actually be downloaded from. So you can see that it's like a range of different topics, right? And the flexibility is what is interesting about the OPA policy engine. It does use a policy language called Rego, which is domain agnostic. It plugs into the Kubernetes admission control hook. So it's an easy way to kind of gate access using that. Now that we've spoken so much about the periphery security, how far have we got in terms of like securing our initial diagram, right? Clearly, I like pink. So everything that has been secured is basically in pink in this diagram. So we had the web application firewall, which we said is kind of right at the entry point before it even hits our API gateway. And as part of the gateway, we kind of extended it where we said we'll do authentication and we will do authorization, right? So now, hopefully we've built a fairly secure, external in kind of system to prevent attackers from outside. How about the internal services? So again, going from the network angle first, right? There is something called microsegmentation that you can do where we basically have applications running, right? Now, every application, let me also caveat this by saying, if it is a virtual machine that you're running your application in, then that virtual machine is actually associated with an IP address and a port, right? So microsegmentation is a way to say your application, when you say secure my application, or you say in this example, in this diagram, you can see that there is a web, there is an app, and there is a database. And if I wanted to write a rule that my web cannot communicate with the database, that's all that I would do. I would say the web can't communicate with the database. What microsegmentation could do is it would convert that into corresponding IP addresses and ports and into network rules to make that a reality, right? And this is actually, this is something that I had kind of worked on in Nutanix. There's a product called Flow where we make this happen. So visualizing this actually adds a lot of value because you want to be able to see what the interactions are to be able to figure out which ones you want to block and which one you want to kind of let through, right? And usually the zero trust model is you start by not allowing any interactions and then start gradually allowing the interactions that you actually want to happen. There is a company called Cilium, which actually extends this model of network microsegmentation to containers. So this is also available in the Kubernetes world now. Now, also, what about the other kind of threats that we spoke about, right? Like we spoke about authentication, authorization, and encryption. And all of this should actually apply even to our internal services, like I said, because you could be interacting between two services within your cloud in the context of someone, right? Like, so I'm still asking you for privileged information, and you might want to know who I am and whether I have access to that particular action, right? The who I am might change a little bit in the service context because you could be, there are two levels of who, right? So there is who am I as the user, as in the customer, the external user, and also who am I as a service. So for example, you could have certain services that you say shouldn't have access to your database. So that's a rule that you can write with the service identity in picture. And the next rule is kind of to encrypt all communications, because like I said, if you have an attacker within, for whatever reason, your system was breached, you don't want it to be an open system that they can completely exploit, right? So going into how we would encrypt all of the communication, right? So there is mutual TLS. So we spoke about certificate authorities. We spoke about certificates being handed and being trusted, right? We, however, spoke about it in the context of just one direction. So the deal with mutual TLS is that both the client verifies that the server is who the server says it is, and the server verifies that the client is actually who it says it is, right? So this is like a small diagram of the handshake to basically say communications don't actually, start happening until both parties have verified each other and communication is completely encrypted. The other part of the encryption story is something called data encryption at rest, right? So all of this time we were talking about encryption during transport, right? Like when you're making API calls or when there is communication, possibly using RPCs or any of that, right? But how about the data which actually gets stored in a database? We would have to actually encrypt that as well, right? And that's the data encryption at rest story. So encryption, of course, happens with some kind of combination of public key and private key. And the other piece of the database, I guess, security story is that you also need access control when you're accessing information from the database. Now, talking more about data, I'm sure a lot of you kind of heard a lot in the news about PII, or personally identifiable information. And this is potentially the biggest threat when there's a data breach, right? Like you don't want your email address or your profile photograph or anything that, or your phone number, anything that personally identifies you to be stored in a way that it can actually be retrieved by someone, right? And so this is kind of a snippet from Amazon's solution. There are a lot of different other ways to do it as well. But just to show an example, you would basically try to not store personally identifiable information in a database which is queryable, right? So there are multiple ways to deal with it. There's something called tokenization that you can do. But this particular example basically talks about how you could have data from S3 being read by Amazon solution called Glue Data Brew, and they would run PII statistics to identify it first, right? And then redact all of that data. And then after that, put it in S3 and then make it queryable. Now, switching gears a little bit, there's also vulnerabilities in the code, right? And essentially, a lot of the code could be a combination of libraries. For example, if you use Golang, you'll end up with like a bunch of different libraries that could potentially have vulnerabilities, right? Or there is open source code that you might be using, or just code that you've written sometimes could have like these vulnerabilities. And I guess I'm going to take an example of probably one of the most dangerous kind of vulnerabilities, and it's called the remote code execution, right? And what this does is the attacker can actually create, malicious code or activity by injecting it through your server, right? So they put malicious code into your website, and then they possibly, run a script or something and gain access into your system or your network overall, and then compromise the system. So what do we do about attacks like that, right? There are a few approaches. So there's code vulnerabilities scanning, which is more of a static code analysis that you keep running. So usually you would have a CI/CD pipeline or some kind of pipeline where your code gets built and deployed and tested and so on. In that pipeline, you would make sure that you also scan the libraries for some vulnerabilities. You could also scan the binaries that you're actually using, right? Another thing to keep in mind is you should apply security patches regularly, right? And this kind of scanning would basically tell you if there's a vulnerability and you need to apply a security patch. And open source libraries, when you pick them up, it's actually good to look at the rating of the library, of course, but it's also important to check what their security practices are in terms of the frequency of their patching and the engagement by the community. There is this project that I found for open source developers, which I think is super useful because it gives you these tools for free to integrate with your open source repo. Now, the other kind of analysis you could do for code vulnerability is something called fuzzing, right? And what this involves is you determine the inputs to any kind of function or any product or service, basically, and you generate data based on the inputs. So fuzz data is essentially potentially malicious data. And then you execute the tests against this data and you analyze how the system behaves, right? And then you start identifying issues based on the behavior that you notice and where there are flaws. Going one step further, there is something called pen testing, where you, of course, set the goals of how you want the overall intelligence gathered. And then you use scanning tools to understand, okay, how a target actually responds to intrusions. And then you actually launch these web application attacks on yourself, right? So you stage it and you try to cover those vulnerabilities, you target those vulnerabilities rather. And then you basically have, maintaining access. So APIs are kind of imitated to see if the vulnerability can be used to maintain the access. So you've gained access, that's great, but how do you maintain it, right? And now from whatever you have learned from this, can you actually apply that to what we spoke right in the beginning about web application firewalls, right? Like, could we actually configure the web application firewall now to take care of these extra vulnerabilities that we've identified? So if we did all of that, then hopefully we will have a completely pink product. So yeah, so ideally what we spoke about the external in threats, and the reason that the services are kind of marked in pink is because we did code vulnerability analysis. We also secured the communication between the services using MTLS and potentially authentication and authorization. We spoke about how the database access could be, like beefed up based on both ODZ, like using authorization and RBAC, but also using data encryption at rest, also making sure that we don't have any PII data and so on.